I started recording. Go ahead.
Thank you.
Yeah.
And display full screen is still not coming through.
Yeah, it was Prem's computer that was sharing, so we let the sharing.
Keep my computer up here so you can see what we can see. Yeah, I can see here, but
Yeah, now it's
perfect.
yeah, I want to.
There's some delays. Let's
There we
get
go.
going. Okay, thank you for the invitation. Good morning, everyone. It's my pleasure to be here at Seagate to deliver this IEEE 1980 distinguished lecture. So it's not very new for the people in Seagate that we have been using magnetic tunnel junctions for reading information. We also have been using magnetic tunnel junction for storing information in MRAM. Today I'm going to show that we can also use magnetic tunnel junctions in the form of domain wall devices to do computing. So this computing is not the traditional digital computing, but it's a new form of computing called the neuromorphic computing or brain-inspired computing. So that's basically the essence of what I'm going to talk. So many of you are experts here, but today's talk is basically like a tutorial, mainly meant for students to be aware of how we can do brain-inspired computing using magnetic tunnel junctions. So it should be very simple for most of you. So with that introduction, let me move on to describe the work. So this talk is sponsored by IEEE 90 Society. Usually I spend some time here, but many of you are already in the Magnetic Society and you are very active here. So I just want you to look at the last sentence. So IEEE 90 Society is a non-profit organization. Please join. This work is done mostly by my students and postdoc in collaboration with people around the world. And I would like to thank all of them. In addition, I also thank the funding agencies, National Research Foundation, and the Agency for Science, Technology, and Research. I'll skip some slides and move directly on to my outline. So as I mentioned, this is mostly a tutorial type talk. So I'll spend around 30 to 40 minutes on the fundamentals and how we can do the neuromorphic computing using magnetic tunnel junctions. Then I'll move on to describe two of the work, one example each for synapses and neurons, which are the building blocks for neuromorphic computing. This is the outline. So you should be very familiar with the two Nobel Prizes that were awarded recently. So one is for chemistry. So these three gentlemen in the picture, they got Nobel Prize for protein structure prediction. So it's, for people in biology, they know very well that it takes 5 years of a PhD student to understand the structure of one protein. And through machine learning, so these three scientists have predicted the protein structure of 200 million proteins. So that's equivalent to 1 billion years of PhD work that is saved by machine learning. So that's the kind of impact that machine learning has on our life. And machine learning was enabled by the discovery from these two researchers. So they came up with the artificial neural networks, which is the building block for many of the artificial intelligence applications that we use as of now. So typically, in artificial neural network, you'll have several layers of neurons. For example, there may be one input layer of neuron, you'll have one output layer of neuron, and you'll have several hidden layers of neurons. So in this picture, all the small circles that you see here, they represent a neuron. And if you notice, this one neuron in any layer is connected to all the other neurons in the neighboring layers and so on. So these connections are not traditional copper wire connections. They also have some weight. So the connections, these neurons, together with the weight, they determine how accurately this network can predict your output. So in the case of advanced applications like ChatGPT-4, these connections can be tremendous. So typically in ChatGPT-4, we have like 100 trillions of such connections. And when we do a query or when we do training, lots of data flow back and forth between the neurons. So that leads to the problem of energy consumption. So in a traditional computing, we have CPU at one place, we have memory at another place. And when we do computing, data flows back and forth between the CPU and memory unit. And especially when you have trillions of connections and when the data flows back and forth, there's a huge consumption of energy. So it's said that in the training of ChatGPT-4, for example, the energy spent is equivalent to taking a car to the moon and back. So that's the kind of energy spent in just training ChatGPT. And for example, ChatGPT-4 is running on supercomputers. So you need water to cool the servers. So the traditional, a typical calculation will yield that one query in ChatGPT will cost like 500 milliliter of water just to cool the servers. And imagine ChatGPT-4 has like 14 million daily users and they all ask queries. So you can see the impact of artificial intelligence on the energy consumption. So this is one of the problems. And if you take the major artificial intelligence milestones, like a human being beaten by supercomputer in the game of international chess. So Kasparov was beaten by IBM computer. Then 2016, supercomputer beat human player in the game Go. And ChatGPT-4, all these major milestones, they use supercomputer. So if you look at the power consumption of a supercomputer, traditional, it typically is tens of megawatts. A supercomputer may be powerful, faster, may do more accurate calculation, but when it comes to intelligent operations, brain is more energy efficient. So it's like 3 orders to 6 orders more energy efficient than a supercomputer in doing computation. So this is the advantage of brain. So people are trying to take inspiration from the brain and try to come up with a new form of computing. So that's called the brain-inspired computing or neuromorphic computing. So since this is a new form of computing, we need new algorithms. So computer scientists and electrical engineers are working on this computing aspect. And as a physicist or material scientist, you should come up with new hardware elements that resemble the components of our brain, like neurons, synapses. All these elements have been prepared, studied and researched by material science. So that's basically the introduction topic. So we are talking about brain-inspired computing. So we should have some idea of how the brain works. So the neuroscientists do not exactly know how the brain does the intelligent operation, but they know that in our brain we have neurons and synapses, and these neurons and synapses are like the computer processors and memory in our brain. So we have a three-dimensional network of neurons and synapses in our brain. So we have like hundreds of billions of neurons in our brain, and they are connected to each other. So in this picture, you will see connection between two neurons. So we have one neuron here, another neuron here. They are connected through something called axon. So this axon is like a copper wire in a circuit. So the electrical signal from one neuron goes to the other neuron through this axon. So this is more like a copper wire. So we'll not spend more time on axon. But let's look at neurons and synapses in detail. Neurons does the processing of information, and the synapses help us to remember the information. And if you look at the brain, we don't have like one CPU and one memory unit separated far away, but we have many processors connected to each other at close proximity to the memory and the next processor. Okay. So this close proximity makes the brain useful. more energy efficient. So this is one of the aspects that makes the brain more energy efficient. Now let's try to understand the neuron and synapses in more detail. So to understand neuron, you can take this water tank as an analogy. So this water tank has many inlets, one outlet, and it also has a small hole through which water may leak. So let's imagine one scenario where we send water through one of these inlets. So water will flow and it may leak. Water level may not rise at all. So that's one scenario. The second scenario, we can consider water flowing through all these inlets. So in this case, even though there is some leak, water level will rise. And once it reaches this level, this will act like a siphon and all the water will be full. So this is the picture you can have in your mind to understand how the neurons work. So in neuron, we have like many electrical inputs that come to a particular neuron. So the neuron will integrate all the received electrical inputs. So if the total signal received by a neuron exceeds certain threshold, it will get excited, so it will fire. So firing is basically producing an electrical output. So a neuron receives electrical inputs, add them together, and if the total signal exceeds certain threshold, it produces an electrical output. So that's how the neuron functions. So to bring out, to reinforce this point, and also to bring out the concept of weight, let me play a video. So this video comes from the Christmas lectures of the Royal Society, London.
There's no audio.
Audio. No audio for the simple.
Oh. I'm not sure how you. Can you turn on closed captioning if we can't get the audio working?
Doesn't look like there's an option for that.
The activation that is high.
Don't look on.
So that's a very simple illustration of how neural networks work. So in that video, for those who couldn't listen to the audio, basically I can explain again. So there were 3 water tanks representing a neuron each. So we have neuron 1, neuron 2, neuron 3. So the first neuron basically determines whether the animal is hairy or not. So she poured beaker with the level 8. So that water level was more than the threshold of this neuron. So this neuron fired and the output went to the third neuron. The second question was whether the animal was heavy or not. So the girl poured beaker level with the water level 9. So that water was enough to fire this neuron. So this neuron also fired. So output went to the third neuron. The third neuron basically received the signals from the 2 neurons and added them. So that's what we call integration. So this neuron integrated the signal, and the integrated signal was more than the threshold of this neuron. So this neuron also fired. So it released water, and that output helped us to understand whether the animal is mammoth or not. So you can understand how the neurons receive signals, and if the total signal exceeds certain threshold, they fire. So that's one thing that can be reinforced with that video. The second concept that we need to understand here is that there were many beakers with different levels of water. So that water level is equal to the concept of weight that we are going to discuss today. So this weight is stored in synapses. So this weight determines how much signal flows from one neuron to the other neuron. So that is basically the point that I wanted to bring from those videos. Now let's say if you want to build a neuromorphic computing circuit, then you need to bring, you need to actually fabricate neurons and synapses in the electronic form. So in the electronic version of neuron, you should emulate all these properties. So if you design an electronic neuron, so this electronic neuron should receive electrical inputs from other neurons, and it should integrate, and it should fire if the total received input is more than certain threshold. So all these properties have to be emulated. In the previous video from the Royal Society, the video leaks, the video misses this property called leak. I mentioned to you that the neurons also leak the potential. So this is also important. So this leak property is explained in this picture. Let's say the value x here represents a neuron potential, and these vertical lines represent signals that come to a particular neuron. So first signal comes at this point, and the value of x changes from some value to a higher value, and there's no signal here, so the value of x drops back to its initial value, and another signal comes in, it changes the value of x, and here there's no signal, so x drops back to its initial value, and so on. So this aspect of the neuron potential dropping its back to its initial value is called a leak. This also must be emulated when you design electronic counterpart of neuron. So this is something that we need to consider. Secondly, now we can move on to understand the synapses. So synapses help us to remember the information. So in brain, we have many neurons and they are connected to each other. And at the synaptic points, we have the memory stored. So if I look at the zoomed in image of this point, you'll see 2 synaptic vesicles corresponding to the 2 neurons in this picture. And when we think something or we do some calculation or whatever, there is a flow of neurotransmitters, chemicals flowing from one synaptic vesicle to the other synaptic vesicle. So this establishes the synaptic connection, and they help us to remember the information. So to understand this point, again, we can take the analogy of 2 cliffs. So I have one cliff here. You can imagine that there's another cliff outside the frame of this picture. So if you want to go from one cliff to the other cliff, you can go down and climb up. That's one way. Another possibility is like you throw a rope from one side of the cliff to the other side. Then with a lot of difficulty, you hang on to the rope, go to the other side. Then when you come back again, throw another rope with a lot of difficulty, you'll come back. But if you do this many times, you can actually build a bridge of rope and you can walk across. So this is how the learning happens. So when a child is born, child has a lot of neurons, but the synaptic connections are not established. So when you stimulate a child, when you make a child go through learning process, then the synaptic connections get established. So for example, if the child goes to the school, then the teacher asks the child to write 1 + 1 = 2. Many times the child writes. So that's like establishing the bridge of rope. So that establishes the synaptic connections, which help our learning and help us to remember the information. So this property can be emulated by resistance. So in electronic circuit, resistance determines how much current flow from one part to the other part. So we can, for synaptic application, we just simply need a resistance, but this resistance should be of multiple value. So it's not something that should have a high or low resistance like in a MRAM, but we need some device that should show multiple values of resistance. So this multiple values of resistance will be equivalent to the weight that we have in the neural network. And this is an electronic circuit. So we should be able to change the resistance of the device, synaptic device, using electrical means. So we should be able to change the resistance with the current pulse or voltage pulse. So these two are the requirement that's needed to consider a material for synaptic application in neuromorphic. So these two properties are very easy to be met. So many material candidates can meet these two properties. So resistive random access memory can exhibit these two characteristics. Ferroelectric materials, phase change materials used for CDs and DVDs, they all can show these two properties. So in fact, in the last 5 years, I've seen many papers to show that their material can do the synaptic properties for neuromorphic computing. But meeting just the synaptic property is not enough. So if you want to build a neuromorphic computing circuit, you need to build neuron as well as synapse using the same material. So in principle, you should be able to deposit certain material and use the same material to make neurons and the synapses. And that's possible by the domain wall devices. Magnetic tunnel junctions in the form of domain wall devices can meet the properties of synapses as well as neurons. So that is the beauty of this particular concept. And people in this audience need no introduction. So magnetic materials undergo at least 2 types of reversal mechanism. So in hard disk media or magnetic random access memory, we have been using coherent rotation reversal mechanism. Then the other form of magnetization reversal mechanism is domain wall motion. So if you apply a magnetic field, then the certain materials exhibit a reverse domain, and the reverse domain propagate by the motion of domain walls. So in this talk, we'll be focusing more on domain wall motion-based devices. And again, the audience here need no introduction about magnetic tunnel junctions. So we have been using magnetic tunnel junctions in the form of Oreo cookie to store 0 and 1. So if you take TM picture of a MTJ, MRAM, it will look like an Oreo cookie. So we have 2 ferromagnetic layers and an insulator layer, stores 0 and 1. But I just mentioned to you that the storing 0 and 1 is not enough for neuromorphic computing. We need a resistive device that can store multiple values of resistance. So for that case, we need to move away from the Oreo cookie type of magnetic tunnel junction to something that looks like a KitKat wafer. Okay, so in this picture, I have a KitKat looking like magnetic tunnel junction. So we have a reference layer. The magnetization of this reference layer is not going to change. We have a tunnel barrier and we have a free layer. and we are going to play with the magnetization of this free layer. So in this particular device, if you send a current through this part, the current will flow through the blue layer on the top, and it will return through this lead. And we can create a spin transfer torque in this region, which can change the magnetization direction of this region from pointing up to pointing down, which is shown by the blue color. So in this picture, the red means magnetization is pointing up, blue means magnetization is pointing down. And when you send one pulse of sufficient magnitude, you can change the magnetization of this region. So you will have a blue domain, and you have a yellow domain wall. And if you apply more and more pulses, you can move the domain wall from left to right. So by doing this, you can create many different resistance states. So for example, you may have fully parallel states giving rise to resistance, low resistance R1, or you can have fully antiparallel states giving rise to resistance R8. And depending on where you stop your domain wall, you can have intermediate values of resistance. This is a concept that we came up long ago, and we proposed this as a memory element instead of MTJ that just stores 0 and 1. This particular device can store 0, 0, 0 all the way to 1, 1, 1. So we can store 3 bits instead of the MTJ. So this was a memory concept that we proposed long ago. Question?
I think it was just a cough in the background. Please go on mute unless you have a question.
Okay, so this is a concept that we came for memory application. At that point of time, we had no idea of neuromorphic computing. But somewhere around 2017, now I'm moving to this topic, a group of researchers from Purdue University, led by Professor Kaushik Roy, they proposed a neuromorphic computing circuit based on the KitKat type magnetic tunnel junctions. So their circuit looks something like this. So they have certain input neurons, output neurons, and synaptic elements. So all these are using the KitKat type magnetic tunnel junctions to do the neuromorphic computing. So this was a theoretical paper. Here, no experimental demonstration of the neuromorphic computing. But since we had proposed this type of magnetic tunnel junction and we are experimentalists, so we decided to jump into this topic and investigate the neuron synapses and neuromorphic computing based on magnetic tunnel junctions in the form of KitKat shape. So that's basically how we entered into this field. So in that paper, they showed 2 types of neuron. One is called a step neuron, another is called a spike neuron. So in the step neuron, you have a magnetic tunnel junctions. You have a magnetic tunnel junction where the free layer and the reference layer occupy the same area. So you have a spin Hall layer at the bottom of the free layer. So when you send a current through a material like tungsten or platinum, you can move the domain wall from left to right or right to left, depending on the current direction. So by doing this, if you apply many pulses, so with every pulse, you can change the resistance of this device. So it will change step by step. And that's why this neuron is called step neuron. Then there's also another type of neuron called spike neuron. So in this case, your free layer has more area than the reference layer. Reference layer is only at the right edge of the device. So you have a reference layer, you have a barrier, then you have free layer. And when you send a current through the free layer, you move the domain wall from left to right, say, for example. So in this case, when the domain wall moves from left to right until it reaches this point, the resistance of this device is not going to change. So you'll see that output doesn't change for a long time. But once the domain wall enters into this region, then the resistance of this device measured in the vertical direction is going to change. So you'll see a change. And if the domain wall goes back, then this resistance will come back to its initial value. So you can create a spike using this kind of neuron, and this neuron is called spike neuron. And we are more interested in spike neuron because the brain operates based on spikes in our neuron. So we are more interested in this kind of neuron. And the synapses they proposed in their paper is very similar to the concept of multi-bit memory that we proposed 15 years ago. So here we have KitKat like magnetic tunnel junction, depending on the configuration, the domain wall configuration, we can achieve multiple resistance states. So that's how we can create synapses. So moving forward, my focus will be more on the free layer of the magnetic tunnel junction, because we are not going to change the magnetization of the reference layer. Barrier layer is also not shown in any of the discussion. We'll focus more on the free layer only. So we are talking about domain wall devices where the domain wall moves, creates spikes, or creates the weights for the synaptic application and so on. So we should know how we can achieve, how we can move the domain wall. So at least there are 3 different possible ways in which we can move the domain wall. In most of the labs, it's very easy for students to apply certain magnetic field, either vary the magnetic field or apply many pulses of same magnetic field, and we can move the domain wall. So that's one way. Another way is to send a current through the ferromagnetic layer and use the spin transfer torque to achieve domain wall motion. The third possibility is to grow the free layer on top of a heavy metal layer, send a current through the heavy metal layer, use the spin Hall effect to move the domain wall from left to right. So if you compare the energy scale, this is very energy inefficient and it's not practical for applications. But in the laboratory, we can do this easily. Most preferable method is the spin Hall effect. So we can, this is the most energy efficient method as of now. And as I mentioned, the motion of domain wall has a different meaning in the context of neuromorphic computing. So if this layer represents a neuron, this neuron will receive electrical pulses from other neurons, accumulate them. And if the accumulated electric pulse is, this electric pulse will help to move the domain wall from one side to the other side. And this is what we call integration. And in the case of synaptic application, let's say this is the free layer of a synaptic device. The current received by the synaptic device will move the domain wall and change the resistance of the device. So that's what we call as weight. So with that introduction, we can understand what we can do as physicists or material scientists. So we can try to increase the tunneling magneto resistance as high as possible. But we have no clear idea how to do this one. We can also come up with mechanisms or materials that can move domain walls at low energies. So currently we are looking at spin-orbit coupling. This is considered to be the most energy efficient. But we are also looking for new ways to move the domain wall. For example, orbital torque has been pitched in recently as an energy efficient way to move the domain wall. So we are also considering this. We can design synaptic devices and neurons and emulate the properties of these devices, like how the brain synapses work, how the brain neurons work. So all these emulations also can be done in the lab. So in my lab, we are focusing on the bottom 3 topics. So today I'll focus more on, I'll give you some example of synapses and the neurons. Okay, so now let's move on to discuss the topic of synapses. So synapses store the weight. Synapses are the memory elements of neuromorphic computing. So for achieving multiple resistance state, we should have a control in how we can move the domain walls and stop at precise position that represent multiple resistance state. But it's not straightforward. So here I show you one example. So this is a lollipop-shaped domain wall device based on cobalt palladium multilayers with a perpendicular magnetic anisotropy. So these are the curve microscopy images So white means magnetization is up, gray means magnetization is pointing down. So here our idea is to create some gray domain in this region and move them controllably, but that's not happening. So we applied positive field, saturated this device with the magnetization up. Then we went all the way to negative 1854 posted. Magnetization still remained in the up direction. And when we change the magnetization slightly, just 4 posted, then this whole device changed the configuration from magnetization up to magnetization down. So we could not stop the domain wall. So during this time, there should have been some reverse domain and it would have moved very fast. Okay. But if there were some pinning sites, this domain wall would have stopped somewhere here, but we couldn't stop because there's no pinning site. So this indicates that domain wall pinning is important for achieving the multiple resistance state in a synaptic device. And this cartoon explains the need for artificial pinning sites. So when we grow a magnetic film due to, say, defects or some changes in the composition in certain regions, we may have some local energy landscape modification. So in this case, when a domain wall moves, it will get stuck here. And if you apply some additional energy, the domain wall can be deepened and moved on. But we cannot rely on the intrinsic pinning sites of a magnetic film because if you make millions of devices, so some devices may have pinning sites, some devices may not have pinning sites. And the position of these pinning sites also will be very random. So we cannot rely on the intrinsic pinning sites. We need to create artificial pinning sites. So if we create artificial pinning sites, we can make almost all millions of your devices to look almost identical. Okay, so these pinning sites can be energy barriers or can be energy wells. So in this case, the domain wall will move and it will get stuck here. In the case of an energy valley, the domain wall will move down the valley and it will get stuck here. And if you apply additional energy, the domain wall will get deepened and it will move further. So that is the concept of artificial pinning sites. And creating these artificial pinning sites help us to make reliable and consistent devices. So we can create pinning sites through many different methods. So broadly, I mean, we have carried out a lot of work in this area. Broadly, we classify them into 2 types. One is called the magnetic approach, so in which we modify the magnetic properties locally, and these regions act like pinning sites. So for example, in this case, we have used ion implantation to modify this particular region. So all these modified regions will act like a pinning site. Or you can use a geometric approach where the pinning sites are formed entirely from lithography technique. So for example, in this case, we have many segments and these segments are offset from each other like a staircase. So in this case, we have some nano constructions. So these nano constructions will act like pinning sites. So you can create these segments in many different forms and you can achieve a domain wall pinning. So today I'm going to show one example, what we call as a fine tree synapse. So as you can see, the name of this particular synapse comes from the shape of the device. So here I'm showing only the free layer of the magnetic tunnel junction. The blue means magnetization is pointing into the plane, and red means magnetization is coming towards you. And this layer is grown on a heavy metal layer. So when you send the current through the heavy metal layer, there'll be a spin-orbit torque, and the spin-orbit torque is the one that drives the domain wall motion. So the domain wall moves from one side to the other side because of the spin-orbit torque. And because of the shape that we have created, there's also an opposing torque called the Laplace torque. So if I create a straight domain wall device like this, then you will not see the Laplace torque. But because of the shape that we have created here, there's also a Laplace torque. So these two are opposing. So if spin-orbit torque is more than this, then the domain wall will move. If Laplace torque is more than the spin-orbit torque, then the domain wall will be thin. And the white region here is the domain wall. And you can see that it behaves like a membrane. You can actually treat the domain wall in this pinning sites as an elastic membrane. And they have the Laplace pressure. To understand the Laplace pressure, you can consider an analogy of a balloon. So a balloon has a rubber membrane. That rubber membrane has a Laplace pressure. So when you would have noticed that when the balloon is small, you try to blow it, you'll find it very difficult. But once a balloon has reached certain size, you want to make it bigger, you will find it easier. Okay. So that because the Laplace pressure of the balloon membrane is inversely proportional to the radius of the balloon. So when the balloon is small, Laplace pressure is high. When the balloon is of a certain radius, larger radius, Laplace pressure would be reduced. So we can see all these effects on the domain wall of this particular device. So we can see them using micromagnetic simulation. So to study the properties of this binary synapse, we carried out micromagnetic simulation. So we created segments to look at this. So we have a region where the width is small. We have a region where the width of the trapezoid is larger. And we keep the length of this segment same as the width of the larger segment. So we varied we studied at least 3 devices where the width is increased from 75 to 150 nanometer. This WS was kept constant. So we studied the domain wall motion due to spin-orbit torque, and we noticed that there are 2 directions. So if you try to send the domain wall from left to right, you will find that you need a smaller current of around 2 times 10 power 11 ampere per square meter. On the other hand, you try to move the domain wall from right to left, you will notice that you need more current to move the domain wall from right to left. So we have an easy direction and a hard direction. And this is coming because of the Laplace pressure that I discussed before. So we can calculate the radius of the domain wall membrane in this particular device. So we have the radius, we can substitute the material parameters and calculate the gamma. So substituting all this, we can calculate the Laplace pressure. Since WS was kept constant, the Laplace pressure for a domain wall that moves from left to right is constant. On the other hand, you try to send a domain wall from right to left, it will have different Laplace pressure. So you need more and more current if you keep increasing the value of WL. So with such a design, when you try to move the domain wall from one side to the other side, domain walls will get pinned here. Okay, so it will not stop anywhere in between. Only these regions will act like a pinning site. So you can precisely decide the position of domain wall. So if this is the free layer of a magnetic tunnel junction, and you have a reference layer, and this will correspond to low resistance to high resistance. So this is the kind of synaptic property that we can achieve through such pine tree synapses. So those are all simulation results. We have also carried out experiments to prove that this concept works. So we made the perpendicular anisotropy. We fabricated devices using optical lithography, so the width is a bit larger. And we made a reference wire and we make devices and shape. And we studied the motion using magnetic field as well as the spin-orbit torque. I'll just show the magnetic field result. So here the number represents the number of magnetic pulses that we applied. And you may notice that in the case of reference wire, this is more energy efficient. With fewer pulses, you can move the domain wall. But the problem will be like, say, in this particular device, 15 pulses have moved the domain wall from here all the way here. But in some other device, 15 pulses may stop the domain wall here or here. So you have no controllability of the domain wall position. However, with this pine tree synapse, this is the position where the domain wall will stop. So you can precisely tune the property of all your devices to have identical values using this particular concept. So that's basically the essence of what we need to do for making synaptic devices. I'll move to the next topic, the lack of time.
Good time check. You got about 6 minutes.
So now let me move on to show the neuron property emulation. So I told you that we need to emulate these three properties: leak, integrate, and fire. So I'll explain first what these three are again. So let's say this device represents a neuron. This neuron receives electrical pulses from all the other neurons. So this accumulated electrical pulse helps to move the domain ball from left to right. The domain ball will move from this position to this position. So that's called the integration. This is not a challenging topic. So people in the field of racetrack memory, they have been studying the domain ball motion by current. So that's not an issue. Fire is basically the domain ball move from left to right. And this region, we have a barrier and a reference layer. So if you measure the electrical resistance through the barrier and the reference layer, its resistance is going to change because the domain ball has entered into the MTJ region. So that's also not challenging topic. People in the field of rate sensors, especially, and MRAM, they have been doing this for many years. So that's not a challenging problem. The unique and the challenging problem is the leakage. So if you use current and move the domain ball from left to right, you stop supplying the current. Typically, you will find that the domain ball will get stuck here, somewhere here. But we want the domain ball to go back to its initial position. So that is the leaky property. So even if you have stopped the current, the domain ball should go from this region to this region. So that is the leakage property. And this is the unique problem for neuromorphic computing. So 5 years ago, people have no idea how to make the domain ball to go from this position to the initial position in the absence of any current. So that is the leaky problem. So we have studied we have studied 4 different approaches through simulation. In simulation, all the approaches work, but experimentally, we have found that 3 of the approaches work. So one is a neuron with an anisotropy gradient. So here, this device represents a neuron, receives electrical pulses. It will move from left to right. The domain ball will move from left to right. But this device has the anisotropy gradient. So physically, it may look uniform, but physical property wise, there's an anisotropy gradient. So when you send a current, the domain ball moves up the anisotropy gradient. But once you stop the current, or once a neuron doesn't receive any electrical pulses, the domain ball will climb down the gradient. So that is the concept. So we have shown that this concept works through micromagnetic simulation and through experiment. The second concept is based on stray field neuron. So here, the top layer represents the neuron. So the neuron receives electrical pulses and the blue domain expands. And when electrical pulses stop coming, the blue domain will go back to its initial position because of this particular design. So here we have a hard layer beneath the free layer, separated by a 3 nanometer thick magnesium oxide. So there's no exchange coupling in the vertical direction, but there's a magnetostatic coupling. So this stray magnetic field favors the red domain. So if you don't apply any current to drive the domain wall, red will expand, blue will go back to its initial position. So that is the idea of this particular neuron. So this design also we have shown metal and simulation results. Then the third concept that we have worked on is a synthetic antiferromagnetic neuron device. So in this case, again, we have 2 ferromagnetic layers, but separated by a ruthenium layer. So there's a synthetic antiferromagnetism. So the synthetic antiferromagnetism favors antiparallel magnetization of these 2 regions. So This case, for example, let's say you send a current through the, it's supposed to play. So if you send the current through the top layer, which is the neuron, the blue domain will expand. And when the blue domain comes here, there will be a change in the resistance. That's what we call fire mechanism. And once the pulses stop coming, the blue domain will go back, red will expand, because energetically having these two layers in the antiparallel configuration is favored. As a result, the blue domain will go back. So that is the concept of synthetic antiferromagnetic neuron. So here again, we have done lots of micromagnetic simulations and also have done experiments to prove that it works. So we prepared films with different ruthenium thickness, observed different magnitudes of exchange coupling. We can tune the exchange coupling. So the exchange coupling strength determines how fast the domain wall will go back. And we prepared devices which look like this. So here the color code is this pink is the bottom ferromagnetic layer, the cyan is the ferromagnetic layer at the top. And we can create a reverse domain here and move the domain wall using the spin-orbit torque. So we send a current through the platinum, spin-orbit torque will move the domain wall from left to right. And we can use the Hall voltage to observe the position of a domain wall. So maybe this will be my last slide. After that, I'll go to the conclusion straight away. So in this example, I show you how we can demonstrate the integrate leak function using magnetic field. So this is field driven. So at first we apply a negative field, high field. So all the magnetization is pointing down. So we remove the magnetic field. So these two go back to the ground state, which is the antiferromagnetically coupled state. And we have a reverse domain here. And when we apply pulses of reverse field, or we can change the magnetic field, we can expand this domain. So this down domain will expand, it will move into this region. So that's what we see here. So by measuring the anomalous Hall voltage, when the domain wall moves from this side to the other side until here, you will not see any change in the Hall voltage. So that's what we see here. But once the domain wall enters into this region, you'll see the Hall voltage is changing. And once the domain wall passes this region, this will saturate. And if you stop applying the magnetic field, here the magnetic field was the driving force. So if you stop applying the magnetic field, these two will go back to the ground state, the antiparallel state. This domain wall will get pushed. So it will be resulting in a drop in the anomalous Hall voltage. So by looking at the Hall voltage, you can know that you are doing the integration and you are achieving the leak. So this region is the region of integration, and this is the region where we see the leak property. There are many results, but I won't go through them in detail. I'll straight away go to the conclusion.
Apologize to Prem due to technical issues. His presentation is cut somewhat short.
Okay. So the conclusion is that the domain wall based neuromorphic computing is more practical. So the material that we use for these demonstrations are the materials already used by the MRAM industry. So it's already CMOS friendly and it can be manufactured easily. Secondly, we are making neurons and synapses with only a small tweak. So using the same material, you do the lithography to have a pine structure, for example, pine tree structure for synapses, make a straight wire for neurons. So you are just by changing the lithography steps, you can achieve both synapses and neurons with the same circuit. So that is the beauty of this particular concept. And I've shown you the emulation of synaptic properties and leaky integrate fire functions based on the domain wall basis. So these are some of the positive outlook that we can have. Moving forward, we may have some bottlenecks, we may have some wish list. So one is that currently we are using spin-orbit torque with a picojoule per bit efficiency. But if we can move towards femtojoule per bit it's better because we are talking about energy efficient computing. So this is one area of improvement. Secondly, this is the one area of weakness of our devices compared to, say, resistive random access memory or other devices, where they have a huge change in the resistance state between low and high level. So they can achieve many weight levels, but with our devices, we may have maybe 8 states. So if you have, say, 10,000 ohms in the parallel state and 30,000 ohms in the anti-parallel state, we may have like 8 different weights. So that's possible. But if we can increase this, I know it's very challenging, but this will be very good. So with this conclusions and outlook, let me end my presentation. Thank you very much.
Let's thank the speaker. Time for one quick question, but we'll have to wrap this up soon. Does anyone have a quick question online? Or in the room? And we'll have conversations offline here. We'll stop the recording there. Let's thank the speaker again. Thanks for bearing with us on that challenge. I stopped the recording.